Hello and welcome to our first in a series of lectures on multiplexer circuits. Right. We're going to see that a multiplexer circuit is known as a selector circuit, and it's commonly referred to as a mux. So if you hear me see the word mux, I'm talking about a multiplexer. Right. Multiplexers are used in communication systems. They're used in CPU systems, so digital logic, we're more concerned with the CPU systems. But multiplexers are used to select which inputs should go through to a desired output. Right? So you're sitting at home sending an email to a friend, right, that lives in another town or across town, right? You have lines within your neighborhood. You have internet lines, physical wires, right? Not everybody has a wire directly from their house to their friend's house. Right? We use a common bus or set of wires. And so messages that we want to send, email messages, are put onto, say, our neighborhood bus, which then might feed into other transmission lines from the city. And they're then put on lines with other messages as well. It's not just our message on the line. Well, there are circuits such as multiplexers that decide then which one of those messages will come through, right? One set of lines will be output at a time. And there's a demultiplexer then that will actually help pull the messages back out into all the various inputs, right, without mixing them up. Right, so we can think of the multiplexer as something where we have multiple input signals, right? And what the multiplexer will do is it will only let one of those signals out at a time. So this looks like there's three signals here, right? There's three different channels, right? But what's happening is at some point in time, likely this F3, that signal was let through first, then this signal was let through, then this signal was let through. Notice how they're going across on one output line. So you're going to see a multiplexer is characterized by many inputs to one output. Right? On the other end, a demultiplexer circuit would then take a look at, right, these signals that are coming in. It would recognize that F3 belongs on channel 3, F2 belongs on channel 2, and F1 belongs on channel 1. So multiplexing many inputs to one output, demultiplexing one input to many outputs, right? Just the opposite. Right. So besides communication systems, and like I said, they're used in computer memory, right? Inside your computer or inside even the printed circuit board for your CPU, you only want so many wires going across, right? And the wires then will transmit multiple different messages, right? If we had to have a wire for every particular message that might come from different areas of the computer, you'd have so many copper wires running across there. Your boards would be bigger. It just wouldn't be an efficient use of space because not everything needs to be transmitted all the time. So we can share these wire resources. Telephone networks use multiplexing as well, right? There's multiple audio signals that'll be integrated into a single line and then pulled off the line by a demultiplexer. So they are commonly used. Right? So again, then in a large-scale digital system, right, your multiplexer is characterized by multiple input lines, right? Only one signal can be placed on one line at a time. So by only one signal, that means the output of the multiplexer. So we have this one signal that comes out, and that's going to be based on a selector input as well. Right. So you can think of, right, the multiplexer circuit is a data selector based on the control line or the select line. So control line and select line can be used interchangeably. That decides which one of these many inputs flow through to the output. And if you think of this as some sort of physical representation of a connection, right, when the selector here in the red arrow is connected to this I0 line, that's what's going to flow through as an output. If you move the selector around, so if this were a mechanical system or something, right, we could move the selector around, and when it's connected to the I1 line, only the I1 line would flow through on the output. So we talk about 2 to the n to 1 multiplexers, right? We've been working in binary, right? So 2 to the n is going to represent the number of select lines. We'll have 2 to the n data input lines. We only ever have one output line. So On the left, number of inputs. On the right, number of outputs. So the simplest example, right, is a 2 input to 1 output multiplexer. And in that case, n is equal to 1, right? 2 to the first equals 2. 1 select line, 1 select bit. Right, so let's talk in more detail about the 2 input to 1 output multiplexer, right? Also known as a 2 to 1 mux, more commonly known as a 2 to 1 mux. Again, 2 to the n data input lines, where n is equal to 1. So they're 2 to the 1 input lines, so 2 input lines, I0 and I1. N select lines, the 1 select line. This is the symbol, right, the logic symbol for a multiplexer, right? The input lines are shown here on the left. The select line is shown here. Sometimes it's shown on top, sometimes it's shown on the bottom, but you always have a select line as an input and data lines. 1 output line, right? And the way the circuit behaves, right, when the select line, in this case, when it's a binary 0, the output will be channel 0, or what's labeled here is I0. So this is pretty easy to remember the behavior of a multiplexer. Whatever the value, whatever the select value is, its decimal value will be the channel number, same as the channel number that's the output. Select is 0, channel number 0 is output. Select is 1, channel number 1 is the output. And that will hold true when we build larger multiplexers such as 4 to 1, 8 to 1, 16 to 1, 32 to 1. Right? Whatever the value of the select is, that tells you what your channel output will be. Right. We can start then by creating the truth table as we have with other circuits. We have defined in this case, we have defined in this case, then there are 3 inputs. There's select, data channel I1, data channel I0, and then 1 output we'll call M. Right. We've already specified the behavior. And so let's fill in the truth table then based on that behavior. Right. So here's a truth table with all the possible inputs. Remember, we have 3 inputs, 2 to the 3rd power, 2 cubed is 8. So there are 8 unique binary combinations of inputs. Right. And what we will see, right, is when the select bit is a 0, what we want to see is that the output M is I0. That's the behavior we specified. When the select bit is 1, we'll see that the output M is I1. Go to the next slide where we have this filled in. Right. So here in red, you can see where the select bit is a 0, the output M is the same as whatever the I0 is, right? So select 0, I0 is a 0, outputs M. Select 0, I0 is a 1, outputs 1. I0 is a 0 here, output 0. I0 is a 1 here, output. Right. So again, when S is 0, the output is whatever's sitting there on line I0. When the select line is a 1, whatever's sitting on line 1, input 1 is the output. So here is the input I1, select is a 1, you can see that the output is the same as I1. Right? That's how we derive our truth table. Right, now that we have the truth table, we can come up with a Boolean expression for it. So we'll go ahead and derive a min-term sum of products for it. Right, and so we can see our 1s are located at, right, min-term 1, 3, 6, and 7. Right. And so when you simplify the circuit, right, and that's left as an exercise to you, you have experience doing that. When you simplify that circuit, you're going to see the equation works out to S naught. So we've depicted then our select line is S, data input line is I1, data input line 1 is I1, I0 is input line 0 is I0, output is M. So S naught, so when S is a 0, that's S naught, and with I0, our output M is I0. Or, so there's our or, when S is a 1, we and then S with whatever happens to be on I1, and we get our output M. Now there's our min-term sum of products equation. If we were to draw the circuit looks like this, right? We've got our NOT gate, our 2 AND gates, our OR gate, here's our M, here's our S naught, here's our I0 coming in here, our I1 coming in here, and our S here. And if we were to build that circuit as drawn and simulate it, here's the output that we would get from a functional simulation. Here you can see in the left half where it's blue, where S is 0, our output M is the same as the pattern I0. Over here on this side, when S is 1, our output M is the same as the pattern I1. So our circuit works as our truth table specifies. All right, I think that is about it for the, oh, not quite, sorry. A couple more slides. So for the 2-to-1 mux, right, what we can say is when S is 0, we don't care what's on line 1, right? And so you'll start to see in some truth tables the don't care symbol for the inputs, right? Here for I1, we substitute that with don't cares because it literally does not matter. We don't care what's on I1 whenever S is 0. All that's important is what's on I0. Similarly, when S is 1, we don't care what's on I0. We only care about what's on I1 because that will be our output. And then we start reducing the truth table to what's called a behavioral truth table. So a 2-to-1 mux behavioral truth table is much smaller, right? We can say when the select line 0, our output will be whatever's on input channel I0. When the select line's 1, our output will be whatever's on input channel 1. So we reduce truth tables to behavioral truth tables whenever we can. All right. So that's it for an introduction to a 2-to-1 mux. Right. The next lecture then will concentrate on ways to represent that in Verilog.